Now, thank you. Um, I've already asked this question, but you guys should. Why is my board off again? Okay. All right, sorry about that. So again, we've talked about dilution, we've talked about this, and I said there was two ways to create a more diluted solution. What were the two ways that you can create a diluted solution? Okay, number one is now let's be a little more specific because you can't always just assume that the solvent is water. So what are you really adding? We're adding the solvent. Now, we can guess and we can assume that sometimes it can be water, but not all solutions are water-based solutions. So you can't just automatically assume that. Because, let me throw a curveball at you. Can alcohol dissolve a solid? How do you know? Pure alcohol. Pure grain alcohol. Nope. I need you to think in terms of chemistry. What would make the molecules be able to make it dissolve? The polarity. What do we know about alcohol? It is polar. So can something polar dissolve something that's solid? Now, here's the part that you have to make sure that happens. It's got to be a very weak solid because the polar forces from the alcohol must be stronger than the bond in the solid. Does that make sense? We know water is very polar, right? It has something called a hydration force. And what is a hydration force? Simplify it really simple. It's the force of water. Really, right? It's the ability for water to create an attraction, and it can break the bond. Well, the alcohol would have to be strong enough to break the bond of that solid. And I don't know of any off the top of my head, but it is possible that it can. So we said add solvent, which we're going to assume is water. And the other one would be to what? Very good. Say it again. Okay. So we could reduce the solute. Now, we have already established that obviously which one is which one is going to be the easiest to do? Definitely add the solvent if it's possible. But I wanted you to understand that the reason this is possible, just reviewing again, that molarity is moles per liter. And mathematically, if you reduce the numerator and the denominator stays the same, what happens to your concentration? It goes down. If you reduce the denominator and keep the numerator the same, what happens to your concentration? Check. My bad. I mean, if you increase your denominator, because we're adding to the solvent. If you increase your bottom value, it still gets smaller. So mathematically, you can do it two ways. But experimentally, the easiest way is to add whatever the solvent is. Now, there's a formula that you need to know, and you should have seen this before, and this is going to be very, very, very important to you. The M1V1 equals M2V2. Now, what do the 1s and 2s mean? Very good. It's what you start it with and then what you end it with. Now, there's two other ways to look at it, and you're going to see one of them right here. And I want you to write this underneath if you hadn't already written it. It's MSVS equals MDVD. Now, what does the S stand for? The stock solution. Any of you work at a big box chain place? Let's just pretend you work at Walmart, okay? If you go into Walmart and there's something, or even Best Buy, we use Best Buy because that seems a little better. If you walk into Best Buy and they say, hey, I'm looking for something and it's not here, where are they going to go check? In the back, in the stock room, right? It's where they hold all of their stuff. So we can take the stock solution, which you have to know is there at the bottom. It is the more concentrated solution. So underneath down there is where it says stock solution, it should be a known concentration. That's going to be the key. So down here, this stock, and I'm going to write it right here, it should be, now anytime I use brackets, what am I talking about? Molarity or concentration, okay? So known concentration. And what we're going to do is we're going to take that stock solution, I'm going to go get it out of the stock room, which is where in this classroom? Through that door. I'm going to go get it out of that room, and I'm going to bring it out here, and we're going to start with it, okay? Should I know the molarity of it? Should I know the volume of it? And then obviously, I'm trying to get a certain concentration from it. So I'm going to dilute it to a certain amount. So I'm going to end up with a certain concentration and a certain volume. Now let me ask you this. Which volume should be higher, the stock or the dilute? Why should the dilute be higher? Because you're adding volume to it. Very good. What should happen to the concentration? It should go down. Does that make sense? Well, I want to talk in math terms, okay? So, preparing your solutions by dilution. The key to pollution is dilution. Often, your solution involves diluting a more concentrated solution. The most common with acids and bases, some of you have seen this. Have I talked about the third version of this formula? Okay, let me show you what it is just in case, and it'll make a whole lot of sense whenever I talk about it. MAVA equals MBVB. If you do not have that written down anywhere, please write that down. Some of you are smart enough to figure this out. What is A and B? Very good. Acids and bases. If you take an acid and you mix it with a base, are you technically diluting that solution? Yes, but in acids and bases, we have a new term. We have a new vocabulary word. What is it called when you mix these two things? No. It is, but there's a certain word that when you mix an acid and a base, you're doing to that solution. Neutralizing, very good. So this is neutralizing. So neutralizing and diluting are identical, but we only use neutralizing when what two things are involved? Acids and bases. It's the exact same process. But when you're neutralizing, what is the major thing that we're affecting that can be talked about in the acid-base chapter? Very good. That is really the reason we call it neutralizing, because what are we essentially trying to do? Make it neutral. That's where the term comes from. Yes, sir. Yes, absolutely. We're going to talk about pH, pOH, Ka, Kb, Kw, pKa, pKb, pKw, all of those things. Okay. I could blow your mind at this point, but we'll get there. Do you want the paper or the liquid? This is the little sticky paper kind. Like you just kind of, whatever. That one just takes longer to dry. This one's instant dry. Well, here. Holy. I need to sign you to a baseball contract. Don't throw that back at me like that. Sheesh. That's instant, not quick. If you mess that up, Peyton, so help you. You could have hurt her. Nope. Now again, so here's the concept of why dilution is important, and this will make sense when you hear it. It's kind of one of those things you have to hear it for it to like click, like, oh, duh, I get it. How many different concentrations of hydrochloric acid can you possibly have? Infinite, right? Do I have infinite room in my storeroom? No, but if I need certain concentrations of hydrochloric acid, is there a reason to have over 30 different bottles of different concentrations? No. So if I have one bottle that's extremely concentrated, can I dilute it to the concentration that I need? Yes. So if I have a 1 gallon or a 1 liter bottle of 16 molar hydrochloric acid, which is about as strong as you can get, which will burn through a table, okay? No, I don't have any. But my point is if I start with that amount, I can dilute it down to a negative exponent scientific notation concentration. Does that make sense? Where it's super, super diluted. So basically 1 drop in 100 milliliters would create those type of things. So it's not practical to keep solutions of many different concentrations on hand. So chemists prepare more dilute solutions for more concentrated stock solutions. So you can start with 1 really concentrated stock and dilute it to whatever you need it to be That is why dilution is very important. Okay, so the tools that you're going to need. Number one is a pipette. How many of you have used a pipette before? Everybody in here should have used a pipette. The one that we're going to use is called a measuring pipette or a graduated pipette. That's the ones, and we're also going to use volumetric or transfer pipettes. I'm going to show you the difference in just a second. So these are going to make it a lot more precise, if you will. How hard is it to get a milliliter in those little plastic pipettes? It's extremely hard, right? You can barely even see the 1 milliliter mark. You do know the bulb, if you fill it up, it's more than a milliliter, right? Okay, it's right there at the neck where the bulb meets the neck is the 1 milliliter mark. So you're only supposed to fill it up to that point to get 1 milliliter. But the measuring pipettes can be a little longer, and they also have graduations, which means what? They have a hat on? Yeah, they have measurements on them, which is why it's called a measuring pipette. Measurements, I totally misspelled measurement. Okay, and a volumetric or a transfer pipette gives only one measurement and 5, 10, or etc. So it's a little bit difficult, but if I asked you to put 50 milliliters of water into a beaker, would it take forever to do it with a single plastic pipette? Yeah, but if I gave you a 10 milliliter volumetric, would it be a lot easier? Yes. Okay. So I just want you to see there are different tools of the trade. So here is a measuring pipette on the left. These are the ones that we're mainly going to be using. Okay. So it has graduation. So if I need you to get 5.5 milliliters, would it be a lot easier? Yeah, because you can follow up wherever it stops. I think most of our measuring pipettes are, 10 milliliters, so you can go up to 5.5. It's a lot easier to get that than doing it 5.5 times with a little plastic ones. Yes, sir. I agree with you. It's just kind of the tools of the trade for chemists. I mean, I see what you're saying. Sometimes and there are larger syringes, and I have a few larger syringes. But most of the time, most syringes come in cc's, which some people don't understand. What is a cc? It's a cubic centimeter, which is the same thing as a milliliter. It's the same thing. Yeah, right. No, thank you. Now, there are two things that you can add to attach to this. So let me ask you something. If I've got a beaker down here at the bottom of this, and I've got a solution in it, can y'all see the top of this thing? Here, let me back it out just to kind of prove my point here. Do y'all see how it's open right here? Okay, so, matter of fact, I'll go get you guys and I'll pass it around so you can see it. Actually, Garrett, do me a favor. Back left corner, it says measuring pipettes or transfer pipettes. Will you get one of those out, please? How would you get the solution into the pipette? Okay, with your mouth. Put a what? Put a bulb on it. That's exactly right. There's actually two things that you can use. Let me pause the video and go help him. Okay. So again, you guys that are passing that around, you can see the measurements, you can see how it works, you can feel and understand what it is to do a volumetric pipette, and it's a lot more efficient than using the small ones. Okay, go ahead. Yes. Yeah. This one right here. Oh. Real quick, let me just throw this since we're still on this page. We will not use one of these. We don't have any of these, so I've never seen one. It's pretty much basically got a line, and it is exactly 5 or exactly 10, and you fill it up to the line. Okay, so let's look right here. What were we saying? Okay, let me look at it, and I will make that distinction now, because I remember what you're talking about. I remember a point where I said change that because that's not true. But let me reread it, and we'll clear that up. Generally, you would measure out the volume of stock solution, such as a 1 molar stock iron 3 nitrate solution that was determined from the dilution formula, and place it in a volumetric flask with a size equal to the think it needs to stay. Did I give a reason why I said to cross it out? All right, let's just pretend for just a second. All right, real quick. I want y'all to look at that slide, but I'm gonna throw this at you. Do you agree that we have a formula called MSVS equals MDVD? Okay, I'm just going to use what they gave us. I'm going to pretend that I need a 0.5 molar of a 500 milliliters of this. Does that make sense? So I'm telling you that I need a solution that's 5 molar and I need 500 milliliters of it. However, in the back, I only have a 1 molar solution. Matter of fact, I'm actually doing this wrong. Why? What is wrong with my setup? Look at the symbols I've used. I have to use brackets. Thank you. You're going to see what I mean with the milliliters in just a second. So, I know that I have this, but my question is going to be what? If I need to create this diluted solution, how would I create it? You've already told me, how do you dilute things? How do you know that? You're getting ahead of me. You're getting ahead of me. I know that I need this solution, right? So, I need to dilute this 1 molar. But how am I going to dilute this 1 molar? I'm going to add water, right? But the problem is, how much do I need to start with of this to create the half molar? So that's my question, right? So really, this is my X. So what you said is 0.5 times 500 is what? 250 divided by 1 is? So X is 200 and, is that right? Yeah, then that's right, okay. Okay. When you said that, I was like, hang on a second, that doesn't sound right. So here's what I would need. I need a 500 milliliter volumetric flask. Why? Okay. This is the final volume. True? And when I'm done, it has to be exactly 500 milliliters. And when I'm done, what should the concentration be? 0.5. Okay? But I'm only starting with 1 molar. So how would I prepare this solution now that you know this number? That's what the words are for. So if we go back and we look at this, generally, if you want to measure out the volume of stock solution, such as a 1 molar stock solution of iron 3 nitrate, that was determined from the dilution formula. So from our problem, how much 1 molar iron 3 nitrate do I need? How much? 250 milliliters. So this is what it says. You're going to take that and you're going to measure out 250 milliliters. And you're going to place it in a volumetric flask with the size equal to the desired total amount. So how large of a flask do I need at the end? 500. So I'm going to put the 250 1 molar into the 500 milliliter volumetric flask, right? Is there going to be room left? Yes. Then what would I do? Add 250 milliliters of water. Or the easier way to say it is to just fill it up to the full mark. Okay? You can tell exactly how much, but you don't necessarily have to. Now the key word is again with deionized or distilled water. That way that you have in the end the solution that you desire to create. Does that make sense? Alright, what's wrong? It's after this one. I just made up those numbers, Devin. The math. All right, so really this is kind of what we're saying, is that a lot of students get confused of exactly where that 500 milliliters is going to come from. It's going to come from the determined, mathematically calculated volume of the stock. Let me say that one more time. It's going to come from the mathematically calculated volume of the stock. And then you're going to have a desired final amount, and that final amount is going to be the amount of water is going to be the final amount minus the stock, which in this case just happens to be exactly equal. It happens to be 250 milliliters. So it's half stock and half water. Is that diluting it exactly by 1/2? Yeah. So if we're going from 1 molar to a half molar, isn't it not exactly half? Yeah, that's all you need. Yes, sir. Yep. Yep. Well, the 250 milliliters is 1 molar. It is the same. Of what? Of water. To get it to 500, and then what you've done is you've taken this 1 molar and you've added 250 milliliters of water. So what have you done? Let me go back to this. Is the what? Yes, exactly. So really, because what we're doing is we're doing the moles of the stock, and we're doing the liters of the stock plus the liters of the water to give the diluted solution. You with me? Okay. Because as soon as you add water, what's it going to do to the concentration? It's gonna make it go down, right? Which is going to give you a diluted solution. Does your moles change? Do they? The moles don't change, because is it still the same number of particles? Yes, but your volume changed, which means now your moles are spread over a larger area, which means your concentration has to go down. See, and that's why I want to get you through this, is that the stock solution volume is what you're going to start with, and you're going to put water in it and make it more dilute. Yep. Okay. All right. So again, transferring solutions. We're going to have the little bolt, the volumetric pipette that I was showing you guys, or the measuring pipette, and it's gonna pull it up, and then you're going to take it, and you're going to. All right. So let's actually start. All right. So I have a stock solution, which means what? Okay, so this is the higher concentration, right? Yes, sir. They do not have to be. Either one. Either one's appropriate. When you're talking in molarity, it has to be liters. But think about this, and I'm going to go back to this just to kind of show you what I'm talking about. So if I do this, let me actually change pages. So if I do 1 molar X equals 0.5 molar times what I say 500 milliliters, if you do this mathematically the right way and cancel that and do 1.0 molar, what's going to happen to your molars? Your molars cancel, leaving you with milliliters, which are appropriate. If you do it the other way, if you transfer this to 0.5 liters, you're still going to get what? 0.25 liters. If I asked you to go get me 0.25 liters, is that a hard thing to do? It's not. If I gave you a liter flask and I said fill it up 1/4 of the way full, okay? But if you think about it, this is much easier. Because if I handed you a 100 milliliter graduated cylinder, you'd have to use it 3 times, but it'd be easier, right? You fill it up once, fill it up again, and then fill it up halfway, and you're done. Okay. So again, use the measurements that are easiest to reproduce by hand. That's really the best way to answer that question. All right, so we're starting out with 2. We're starting out with a stock solution, which is the highest concentration. Why is this second jar empty? Okay, this is going to be our dilute solution. Okay, let's just pretend. Well, it's really not a good. It's not really good way to do it. So we're going to try to create a dilute solution with a known concentration, right? So what am I going to do with my stock? I'm going to calculate how much I need of it, and I'm going to put it in my dilute solution, right? Okay. Then what? That's when that formula comes in. So the how would I know the volume that I need? No, mathematically, how much? Oh, I did that wrong. Used the wrong letter. How much volume of the stock solution would I need? Do you agree that's what I would do? Okay, if I know the concentration of my dilute and I know how much of it I need, should I know the concentration of my stock? So one more time, let me do this while you're looking at it. My diluted solution, do I have to know the concentration I'm trying to create? Should you know MD? You should know MD. Do you know how much of your dilute solution you need? You should know that. Do you know the exact concentration of your stock solution? Yes, I know that as well. So I can determine how much volume I need. Does that make more sense? Yes? Okay. So I'm going to pull it out. I'm going to put it over here. So right now, I have what in the bottom of this right middle volumetric flask? Do you agree that that is just my VS? That's my volume of my stock solution, right? Now, how do I take that stock solution and dilute it? What is this? We're just going to pretend that it's water. Or acid, if you want to make it acid. Okay, so that's how we would create. Visibly, how can you tell that it is more dilute? The color change, right? So we know that it is now less concentrated because there are less moles present because of there's more volume present with the equal number of moles. So it's going to spread it out. So does this picture help? It does? Okay, good. So again, you start with a stock solution, you take out how much you need based off of calculation, put it into an empty flask, and then fill it up with water. That's all you do. That's how you dilute a solution. Okay? Alright, for making acid dilutions, it's technically okay to do the same process as ionic solutions as long as the stock acid isn't concentrated too much. So again, I'm kind of just throwing this at you now because our acid's dangerous. Yeah, so we need to make sure we take a little bit extra precaution. If I give you some potassium chlorate solid, is it going to hurt you if you get some on your skin if it's a solid? No, you just wipe it off and you move on. But if you take 16 molar hydrochloric acid and pour it on your skin, we've got problems. What's wrong? You have your iPad? Here's what I would do. Let me pause this. Not break down those plastics. Alright, so again, let's talk about this. Sulfuric acid is the really bad acid about generating heat, and again, this is the Breaking Bad thing that y'all talked about, and we talked about how plastic is the reason that they put it in plastic because it won't dissolve it. Generally, if you're doing the acid dilutions, instead of starting out with an empty flask, start with about half of the amount of water. And here's the reason why, and I don't know if it's on this slide or the next slide. If it's not, I'll go back and add it. And this is the reason why right here. You never ever add water to acid because it'll make you go wham. It splashes and it creates an extremely exothermic reaction. So when it starts getting really, really hot, two things can happen. It can splatter and it can splash, or it can crack the glass and then you have it everywhere. So here's the way I'm going to put this to you. If you work at McDonald's, would you take the hot grease and dump it on the bag of fries? Okay, so our Arby's connoisseur right here. But would you take hot grease and dump it on the bag of fries? That makes absolutely no sense, right? But you do take the fries and you put them in the hot grease. So we're going to treat acid like it's an extremely hot solution. Okay? It may not be physically to the temperature hot, but it can create exothermic reactions. So we're going to take it with the most precautions. You with me? So how do we treat acids in water? You add acid to water. All right. If I have a lot of water and I slowly add acid to it, if it creates an exothermic reaction, is the water, since the water is in higher concentration, will it absorb the heat being produced? Yes or no? Yes. Vice versa. If I have a lot of acid and I start pouring water in it and it starts creating an exothermic reaction, is there anything there to absorb the heat being produced? The glass. And what can happen to glass? It can shatter. Then Peyton's in trouble. Because if we ever do this and you do it wrong, Peyton's in trouble. I just need you to understand. You take your acid and you pour it into water, not the other way around. That's the whole gist of this. Okay? Always add acid to water. Okay? So, problem. What volume of a stock, now when it says stock, what does that mean? Okay, very good. This is, come on, Mr. Penn, this is the most concentrated. Okay? So what volume of the stock solution of hydrochloric acid is needed to prepare 250 milliliters of a 3 molar hydrochloric solution? So let me ask you something. Stock versus dilute. What if they had never told you this word? What if they just said, what volume of 11.6 molar hydrochloric acid is needed to prepare 250 milliliters of a 3 molar hydrochloric acid solution? Simply based on the question, without the word stock, could you still determine the stock solution? How? A higher number. I need you to know that. They're not always going to say, here's your stock, here's your dilute. You've got to be able to read through the words of how they use them and be able to understand that. So what are they specifically asking for? What volume of the 11.6 molar solution? So technically we're solving for volume, right? But which volume? The stock or the dilute? We're solving for the stock. So I'm just going to write it like this. So MSVS equals MDVD. And I'm going to kind of quiz you real quick. I would like for you to algebraically rearrange that for VS. And I pray that you can do it. Don't say it out loud. This is the part that scares me about this class, is that some of you don't know how to do this algebraically. Do what? What? Got to take the derivative and the integral of it. Good luck. They're the opposite. The asymptotic. I didn't talk to her. Alright. So I've got the molarity of the dilute, which is 3 molar. I've got the volume of the dilute, which is 250 milliliters. What's wrong, Peyton? Sarah, why are you drawing her pictures? Peyton never pays attention. Peyton, you're going to be famous in these videos. Should send it to your mom. Oh, wait, I do. Nothing. Alright, so, when you do this math, has someone done this math for me? Okay. Alright, so 64.7 milliliters. Now, here's the important part. If I handed you an 11.6 molar bottle of hydrochloric acid, and I said, go do this. There's something very important, Peyton, that you would make sure that you have to do. Put what in first? What are you pouring into what? Okay, you should pour the acid into the water. Now, how big of a flask do you need at the very end? Like, what is your total volume of your final flask you're using? You're using a 250 milliliter flask. So let's just pretend that we've got the Erlenmeyer flask, and it is exactly 250 milliliters. Okay, so this number that we're talking about right here, this number that we're talking about, what is this number technically going to be? Is it? It's the volume of what? Okay, it is this. I need 64.7 milliliters of that very strong acid. But it's like we've already talked about. Are you going to pour it in and then fill it up? No. What did the thing say? Fill it up about halfway. Can y'all see that color? Let's make our water yellow. That's a little weird, but that's okay. Actually, yeah, acids are a little yellow. So that's actually really bad. Let's make our water orange then. I wouldn't drink it if that was... It's kind of what our water looked like before we moved out of these labs. Hold that thought. Yes, sir. All right, say that one more time. To this one, to 3. Basically, we're fixing to do a lab where I need a 3 molar hydrochloric acid solution. I'm creating it to use it for something else. Whatever the reason to have 3 molar is, there's got to be a reason for 3 molar concentration. For any type of lab. I mean, I can't give you one on top of my head. Any lab that you would need, if I need to do a titration lab, but I need a 3 molar hydrochloric acid solution, if I'm trying to titrate it with, which you don't know what titration is, if I'm trying to determine the titration curve with 3 molar versus a 3 molar sodium hydroxide, I would need exactly 3 molars. This is a way to get exactly 3 molar. Okay? That's weird. Food coloring? That sounds weird. So again, what we're going to do is we're going to take some water, we're going to put it in there, and we're going to go drippy, drippy, drippy. And we're going to add drippy, drippy, drippy. And we're going to put some acid in there. But exactly how much are we going to put in there? 64.7 milliliters. And if it's not full, then you fill it up the rest of the way. Okay? So that's what you would do with this solution. All right, you guys figure this one out on your own if you hadn't done it, please. All right, so here's my question. What are you exactly solving for in this question? Very good, because it says what is the final volume. And whenever you're doing a dilution, the final volume should be VD. So we're solving VD equals MS VS over MS. Okay? Now, we know that, but then based off of what we have, it never, well, it does say, and I hate that it says that. My bad, thank you. I always mess up my letters. MD. So, what would the final volume of a solution be if 50 milliliters of a 0.5 molar NaOH is diluted to? Nope. So let me ask you something. Let's pretend that they eliminated the word diluted, and let's just say it was changed. It's changed to a 1.25 or 0.125. How could you know which one was the stock and which one was the dilute? The bigger, the higher value is which one? The stock solution. Okay. So we've got a concentration of 0.5 molar with a volume of 50 milliliters, all divided by 0.125 molar. So, what would that answer be in 3 significant figures? 200? Yep, thank you, very good. 200 even milliliters. How big of a flask would you need? 200 milliliters, right? How much of the stock solution would you put in first? 50 milliliters. So you'll put the 50 milliliter stock solution in, and then do what with it? Add 150 milliliters of water, right? No. Huh? This is base. This is NaOH. So all right. So let's just draw it out. So what we're doing is we're going to take. So we've already said that this should be a 200 milliliter volumetric flask, right? So what we're going to do is we're going to put the base in, and this is 50 mils of NaOH. Well, how much water do I need to fill it up? It is, but it doesn't matter. This is 50 milliliters of NaOH. How much water do I need? I need 150 milliliters of water. Okay, so again, that is exactly what you would do, and it's going to dilute it down to the 0.125 moment. Okay, so do y'all think you pretty much get this? Does this make sense? Is it easy? What if I call one of you up to do this problem? No, you take forever. Brianna. Full pepper. Can you do it, Mary? All right, guys, y'all practice on this one. Okay, Mary, tell me what to do. Tell me what to solve for first and how you know to solve for it. Okay, why am I solving for MS? Okay, that's the original. Now, and again, I'm throwing different words at you to make sure you understand what the words mean. Original means the stock solution. So MS is equal to what, Mary? Very good. Okay, so what was your MD? MD. Okay, and what was your VD? Okay. And then what was your VS? And what did you get for your final answer? 1.51. Okay. And that is molar. So, Claire, how would you actually do this? How would you actually make that solution? What would you do? Tell me what equipment and how much. Tell me how to draw it out. How much? How big? And what kind of flask? Volumetric? How big? Why? But how much of a solution are they asking you to create? What's the first word? That's how much they're asking you to make, right? So you need a 300 milliliter volumetric flask, right? Okay, what are you going to add first? You're going to add all the water? You're going to fill it up? What do you have to add first? Add the dilute solution first. How much and what concentration? Do you have your dilute? You gotta have how much stock? And how much of it? Actually, it's gonna be more like this. What concentration? What is the concentration of your stock solution? That's what you just solved for, right? Because you solved for molarity of stock. You with me? So, I'm going to put in 250 milliliters of a 1.50 molar stock solution. Now, Claire, how would I finish this solution off? I'm not full. Add what in? I've already got my stock solution. How do I dilute it? How much water? Okay, which would be... Come on now. No, you're right. 300 minus 250. 50 milliliters of water. So, would that dilute this solution to 1.25 molar? Yes. Does that make a little more sense? You sure? Okay. You've just got to be able to read what your units are in your problem to figure out what all this is, okay? You will never be able, none of the problem will ever tell you exactly how much water to add. You would have to subtract that to figure that out. Okay. All right. So, yes, sir. All right. So, we're starting with, in this problem, we're starting with a base, right? We're not going to talk about bases. We're talking about acids. So let me go back up. Whenever you're trying to dilute an acid, okay, instead of, let me just draw it for you. Let's pretend that I've got a 200 milliliter volumetric flask, okay? What I do not want to do is add, let's just say, 50 mils of HCl, okay? I'm going to dilute this solution to something. I do not want to start with this and then pour H2O in. Okay, the reason why is there more acid in every second until a certain point. You see what I'm saying? Because every time you drop a certain water molecule is a reaction going to occur. Yes. So what's going to happen is every time a water droplet hits this thing, a reaction is going to occur. Some of these reactions create exothermic reactions, which create a lot of what? Heat. So if you put your acid in and then slowly drop by drop add your water to it, there's going to be an immense amount of heat given off, which could cause two things. It could splatter or it could crack the glass. And once it cracks it, it spills. So this is not the method we want to use. What we want to do is if we're adding acid to it, and we know that I tell you I needed exactly 50 milliliters, what I would do first is I would add about 100 mils of water. Now, when you take that acid and you drop it in, there's enough water to absorb that heat that's going to be created. So instead of the glass absorbing it, the water absorbs it. And so then once you do that, you would end up putting in your 50 mils of HCl. Well, that's still not enough, right? That's 150. And so then what would you do? Add 50 more, and then you're done. So it's just one additional step. So instead of going ahead and pouring in the stock solution, you put a little water in first, and then pour the acid, and then fill it up. So it's one additional step. So you only add water first if it's an acid. Okay? Yes, sir. Yep. And the reason why is because of that exothermic reaction that could potentially be created, which could cause a dangerous situation. Got it? Okay. All right, what I want you all to try and do is this next problem all by yourself. Explain how to make this solution. You've got to have math and you've got to have words. If I'm going through this many times, you're probably going to see it. Yeah, you're probably going to see it again. I would know how to do this. Okay, go ahead, Devin. Explain.
Using a 100 milliliter volumetric flask.
Pulse. How do you know it's a 100 milliliter volumetric flask?
He's on
problem is, explain how to make a 250 milliliter solution. So, if you use 100 milliliters, do you have enough space to create your solution? How much are you trying to make? So you would use 250. Use the size, and again, Brandon, that's where I went back. So we do use the size of the flask. Yes, sir. I'll set off whenever we're done. Once we get it all done, I'll write it. Okay. So we want to use a 250 milliliter what? Volumetric flask. Okay, go ahead.
And then I added stock first.
Okay. You add stock first.
3.5 concentration.
Okay, a 3.5 molar. How much? How much of the stock solution?
3.5.
That's the concentration. How much volume?
Oh, 71.4.
Very good. Okay, so you're going to take 71.4 milliliters. Let me actually do this with you. Okay, so you're going to measure out 71.4 milliliters of, whoa, that wasn't very nice. No, it's because he moved the mouse. Okay. Measure out 71.4 milliliters of a 3.5 molar. What is it? NaCl? Okay, thank you. Of a sodium chloride solution. Okay. This is how much I'm going to start with, right? This is the volume. This is the volume and the molarity of what specifically? Of a stock solution. This is what I got out of the back room. Okay. Then what I'm going to do? What am I going to do with this solution? Okay. Pour it into a what, Devin? Thank you. 250 what? Milliliter volumetric flask. You can. If you want to use those adjectives, that's absolutely fine. Slowly, carefully, transferring it with a pipette. But if you're having to do 71.4 milliliters, that would get tedious, right? Okay. No, absolutely not. They're looking for your numbers and the laboratory description to make sure that you're doing it appropriately. Okay. How you would essentially word it is up to you. Yeah. Okay. Yep. Pouring it in is fine because they assume that when you pour carefully. Okay. So we're going to pour that into a 250 milliliter volumetric flask. Then what are you going to do? Okay. Add enough. Say that key word again, Brianna. Distilled, or what's another fancy word? Pure? No. Deionized. To fill to what point? The 250 milliliter line. Ooh. Now, you could period in sentence and go to the next question. I'm one of those nerds that on May 2nd, I would add this next sentence. Again, now, yes, but I want you to understand what I mean by this. Do you agree that you're creating something? What's one other sentence that you could summarize and give this full credibility to finish off? Bingo. To create a blah, blah, blah solution. That's exactly right. Okay? That's the one extra punch that you can throw in to say, I know exactly what I'm talking about. Okay? I would actually, 2, comma, is that even right? Okay, 2, create a, and I don't even know what it is. What is it? What's the constant? Thank you. A 1.0 molar NaCl solution. I don't know. You guys fix it grammatically. I'm not the grammar police. No, we're chemistry teachers. If you, we're happy if you spell it right. You are officially in the dumb category. You want that back? Anybody want that back? Okay. All right, this is pretty much the exact same thing. I want to move on to one more. Somebody help me out real quick. What is that first sentence? Just the top sentence. All right, hang on. Pause. Sarah, read it for me. Oh, this is a good one. Okay, let's hear this one. An effort to conserve materials. Now again, we want to do conserve materials. So we're going to combine 2 bottles of H2SO4. Okay? One bottle contained 350 milliliters of a 3 molar solution. The other bottle contained 1.5 liters of a 1.25 molar solution. What is the molarity after the assistant is done mixing the bottles? This is a really good question, and I want us to see the answer, but I want to actually double check and make sure. I want to get the key out because I don't want to make sure I mess this up. Yeah, I don't want to make sure. All right, guys. So let's tackle this one because this is a good question, and I want to make sure that you understand this because this is something that could affect you in the real world. So here's what I'm going to do, guys. Y'all listen for a second. I'm going to take a flask. I'm actually going to take 2 flasks, and I'm going to create the situation. Okay. All right. So one of these flasks is 350 milliliters. Yes, ma'am. Thank you. I eat both. You're so sweet. Why am I not surprised? I am so not surprised. Okay. All right. Stop. So we've got 350 milliliters and a 1.5 liter. The 350 is a 3 molar, and the 150 is a 1.25 molar. All right. So here's the deal. What is essentially the question they're trying to get answered? After mixing, right? So really, it's the question, and it's in simplest forms, is what is the molarity? Is that really the question they're trying to get you to answer? All right, so let's look at it from that perspective. So we know that molarity is what by definition? Moles over liters. Well, let's think about something real quick. This should make a lot of sense. Are we adding 2 solutions? So let's start with the easiest one first. When you add 2 solutions, does your volume change? Yes. Will it affect your molarity? Yes. So what can we do with our 2 volumes? Add them together, right? So that's the easy thing. But the problem is, are they in the same unit? No. So let's convert one of them to the correct unit. So this is going to be 0.35 liters, right? So let's go ahead and let's write this in. So the liters are the easy part. So we've got 0.350 liters plus 1.50 liters. Now I'm just going to write this number under it just to make it easier. What is the answer to that? Okay, 1.835. Why not say that? 0.85. Why not? Yeah, you said it and I started writing it. 1.85 liters. So, do you agree that's the easy part? The difficult part is knowing where to go from here. When I take these 2 solutions, I've got a bunch of particles running around in here, right? Now, let me ask you, here's kind of a tricky question. You got to think, which one of these has more particles in it? Why? And I actually did it backwards. Sorry. How do you know the one on the left? It's got a higher molarity and a what? And a lower volume. So it's even got way more than that because of this relationship. The higher concentration and a smaller volume yields should be higher particles. So, do you agree that concentration is moles divided by liters? I've got to find out how many moles are in this thing when it's mixed. So how can I find the moles after it's mixed if I have both of the volume and the concentration of the solutions? Whoa, 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 whoa. Why would you do molarity divided by volume? Very good. Because remember, and I'm just throwing this up here just for help, molarity is moles divided by liter. Okay? So, the track you're on is right. The mathematical part's the part where I don't want you to mess up on. So, what you were saying, now that you know the math, what would you do with this? But what are you solving for? If I have the moles of this and I get the moles of that, what can I do with both of them? If I add them together, would that give me my total number of particles in both moles plus moles? Does that make sense? Okay, so I know the number of things floating around in the solution. I know the number of things floating around in this solution. And so then all I have to do is just add those two things together to get really moles total. Let me change that color so you can see it. Moles total and liters total. Because that's what I'm doing, right? I'm adding two things together. So let's look at this. So it is going to be, was it 3.5 or just 3? It's 3 molar times 0.35 liters, which gives me a value of 1.05 moles. And we're going to add that. And this one is 1.25 molar times 1.5 liters, which gives me 1.88 moles. And so my total moles is 2.93 moles. So now, from both solutions, do I know how many things are floating around? Yes. So what I do is I take this number, 2.93, and I plug it into my moles total. So 2.93. And divide it by what number? 1.85, which gives me a final concentration of 1.58 molar.